Okay, so you may recall that last class or last lesson we created scatter plots and we found the equation of the least squares regression line, but now we have to start to ask a question, and you may say, gee, Miss Cooper, why do you have the book here? Sometimes it's actually important that I read the book with you so I can translate. So now this question of, all right, you've created a linear model, a least squares regression line, but is it appropriate? Is it the best fit? And I like what your author says here. Just because your correlation coefficient is strong, does it mean that the relation is linear? No. And the author blatantly says to determine if a linear model is appropriate, we need to draw a residual plot. So today we're going to be working on residual plots, which is basically a scatter diagram with the residuals on the vertical axis and the explanatory variable on the horizontal axis. If that sounds scary, it's not. I'll do it with you in a moment. Okay, the biggest thing I can tell you is anything in a purplish, bluish box in your book like this is very important. Math books are always like that. They put the important stuff in these magic little boxes, right? So, okay, so if a plot of the residuals against the explanatory variable shows a discernible pattern, such as a curve, then the explanatory and response variable may not be linear related, i.e. there may be a better model, like a quadratic model or exponential model, something like that. Now, we're not in a math modeling class, so we're not going to go through all those models, but we're just going to say, hey, is the linear model appropriate or not? So let me actually show you a picture of what I'm talking about, which would be in the next page of your book. Okay, so with this example, you can see that it's just two examples of residual plots, okay? Here's a residual plot where there's no discernible pattern, and the author is reminding you that a linear model is appropriate. So you see, here's the zero line. I'm just going to highlight that. And basically, you have sort of evenly dispersed, patternless dots above and below the zero line. But here, this is not patternless. You sort of have this U shape, okay? So what we say is then if that is the looks of the residual plot, then the linear model is not appropriate. You have patterned residuals. Now you may be saying, all right, well, how am I going to make this residual plot? Don't worry about that. We'll deal with that in a moment, okay? A little bit more in terms of terminology here. Let me turn the page. Okay, so I moved to the next bluish box in our book, and again, I'm just pulling these boxes because they're so important. So it says, is the variance of the residuals constant? If a plot of the residuals against the explanatory variable shows the spread of the residuals increasing or decreasing as the explanatory variable increases, then a strict requirement of the linear model is violated. The requirement is called the constant error variance. A fancier term, I like the way your author says that in fine print, a fancier term for constant error variance is homoscedasticity. Okay? All right, I'm going to hit pause and we'll take, what does that mean? So this idea of the spread of the residuals increasing as the explanatory variable increases. So if you're a visual person, you need to see it. So here is, remember last time we talked about scatter plots? So here is just a basic scatter plot, x against y. But over here is the residual plot that belongs to it, okay? And what's basically happening is that as x gets larger, as x tends towards infinity, these residuals, notice you kind of have this horn shape, this trumpet shape, right? The residuals are becoming further away from that zero line, and I'm going to draw that zero line in another color. So remember, here's 0. So basically, as x tends towards infinity, residuals move away, either become increasingly large or increasingly small. In this case, in this visual here, the residuals are becoming increasingly large. So that's another case where we say, all right, the linear model is not reliable, and in fact it's in violation of one of the constraints. Okay, now the only way for us to wrap our head around all this is to actually do an example. So I'm going to pull one from the book. And, as a stats student, I hope you would do the same, that you would be pulling examples from the book that you thought you should work. 25, well, Kepler's law of planetary motion. is a good one for us to work through together. So I'll read it. The time it takes for a planet to complete its orbit around the sun is called the planet's sidereal year. In 1618, Kepler discovered that the sidereal year of a planet is related to the distance the planet is from the sun. The following data shows the distances of the planets and the dwarf planet Pluto from the sun and their sidereal years. So basically, the author's nice in telling us, let's let x be the distance from the sun and y be the sidereal year. So they're basically telling us the x and the y. For you, in terms of using your graphing calculator, let's let this be list 1 and this be list 2. Okay? So what I did, I just wanted to show you the data. I put the data in my graphing calculator, but I wanted to first flip to the next page where you can see all the things they're going to ask us. Okay, and this is why this is a great problem to practice for, say, a test. And I'm just going to read it through to you here. These are all the parts that belong with this. So they want us to draw a scatter diagram of the data, treating distance from the sun as the explanatory variable. So long story short, scatter plot. Part B, we want to get a correlation coefficient, the correlation between distance and sidereal year. And then it says, does it imply a linear relation between distance and sidereal year exists? Okay. Then it says compute the least squares regression line, so all of those things we did last class. But then it says plot the residuals against the distance from the sun. That's a residual plot. We haven't done that yet. And then it says, do you think the least squares regression line is a good model? Why or why not? Right? All right, easy goes. Let's pull up the, I'll hit pause and I'll pull up my graphing calculator to do all these things. Okay, so hopefully you can see pretty good what I'm doing on here. So recall that you go to Stat and Edit. And by the way, you can do everything I'm doing in Excel. I'm just using the graphing calculators because a lot of schools use those. We use them on tests. So you'll notice I put the distance from the sun as x, and for y is the response variable, the sidereal year. So basically I put the data in L1 and L2. If you need to rewind the podcast and go back and look at that data, that's fine. But I really wanted to focus, and let me scoot this over here, I really wanted to focus on part A, which is draw a scatter diagram. Okay, so I'm going to hit second stat plot. I'm going to hit enter. I'm going to highlight the one that looks like a scatter diagram by hitting enter. Okay. L1 and L2 by default, that means that's why I always keep my data in L1 and L2 so I don't have to mess with that. Okay. And remember, the trick is to hit zoom stat to view your scatter plot. So, aha, I see it looks like a very strong linear relationship. Just by guessing, without even running it, I'm thinking, I don't know, 0.97 something for the correlation coefficient. But strong positive association is what we could say for starters. Okay. Then in part B, it says determine the correlation between distance and sidereal year. So that basically means get little r, the correlation coefficient. All right, let's do that. Stat, calculate, slide down to linear regression, and if you just hit enter, it knows that you have your information in L1 and L2, so by default. Okay, and just as we thought, your correlation coefficient is very strong, 0.99, well, 0.9888, so right here, little r. What I want to do, though, and let's see if I can do this here, I want to retrieve the equation. So make sure you can practice writing the equation. So the least squares regression line in part C, let's just practice writing that. I call it y hat. So it's like y equals mx plus b in algebra, except the calculator's calling it y equals ax plus b. But it's telling you this a is your slope, so that's 0.0657 x, and then plus b, but my b is negative 12.5, so I'm going to say minus 12.5. Okay, so basically that's my y hat. That's my least squares regression line. So that'll satisfy, C, compute the least squares regression line. Okay, then we have to walk through what we did before. We have to walk through what we did in class last time, basically, to get all the residuals. Okay, I'm going to hit pause. Now, it's not asking to do this, but I always think it's a nice skill to have, is to run your equation through. So let's go ahead, now that we have the equation, and I just, sort of wrote it down on paper so I could copy it in here. It was 0.067x, so 0.067x 0.067x, and then it was like minus 12.5. And again, I chopped that off, those decimals. Oops, 0.0657. X, and then minus 12.5. Okay, so now I have it in there, and I always like to just hit graph and just see, and it's like, yeah, at least the regression line doesn't live way above or way below those points, so it looks accurate, even though I chopped off some of those decimals. Okay, now we're ready to go in and get the residuals, because we need to create a residual plot. So remember, residuals go on your y-axis, and your explanatory variable is going to go on your x-axis when you eventually go to do the plot. So remember that residuals, and I can write that on here. Let me get my pen going here. Remember that residuals is y minus y hat. So it's basically your observed values of y minus your predicted values of y. So I'm just going to circle this. These are my observed values of y, and I'd like to get my predicted values of y, my y hats. I'd like to get them in L3, but I'm going to have to write a command to do that, right? Okay, so let's try that. So I'm going to go over to L3, and I'm going to command L3, and that's where I'm using that regression line. I'm going to take 0.0657, and I'm going to tell it, second L1. And you say, why, how come? Because I need to store all the x values for x into the least squares regression line and get predicted values of y. So you see that the command is 0.0657 times L1 and then minus 12.5. So if you're wondering, and I'll pull up the magic pen here, I'll zoom in. It's basically, in terms of command writing, it's basically like I used, L1 in place of x, right? So what that'll do, just like you're writing something in Excel, it'll do all the number crunching for me. So let's just go ahead and hit enter. See, so now what it did, it got, in L3 basically, I now have my y hats. So I'm still not at my residuals yet. So now, in L4, I need my residuals. Let me clear out what's in there. In L4, I need my residuals. So what are residuals? It's y minus y hat. So in terms of command, it's L2 minus L3. And hit enter. Aha. Now you got your residuals. Now, final frontier. We want the residual plot. Remember, if there's no discernible pattern on the residual plot, the linear model is a good idea. If there is a discernible pattern on the residual plot, the linear model is not a good idea, and you should try some. There's a better model out there. Okay? So, now remember, residual plot is your x variable against your residuals. So my x variables were in L1. So second stat plot, oops, try that again, second stat plot, hit enter, and the thing is, I have scatter plot highlighted. L1 is my x data, but L4, because I'm plotting against those residuals. Notice I told it L4. Alright, zoom, stat. And so just like the, oops, I want to make sure you clear anything out of there. Now, just like the author said, now let me highlight this. Remember, the author said that a residual plot is simply just a scatter plot, but let's see if I can do this in another color. You've got your y-axis here is your residuals. For some reason, it's not letting me draw on it. But you see, basically, long story short, there's definitely a discernible pattern. So, final answer to this last part here, do you think the least squares regression line is a good model? I'd say no, there's a better model out there because there's definitely a discernible pattern on the residual plot. Okay? Hope that helps. And good luck with your residual plots. The next thing that we'll be looking at is conditional distributions.